So just to recap what we were talking about, we said that as opposed to GSM, GPRS uses a 52 multi-frame structure, and on each time slots we have 114 bits. And then we also said that there are 52 frames, and a radio block is essentially 4 time slots or bursts from 4 consecutive frames in the same carrier and in the same time slot position. So altogether we can transmit up to 456 bits of information in one radio block. Okay, and this number 456 will come up later in some of the diagrams we'll see. So you'll know that it comes from here. So 456 is essentially 114 into 4, because there are 4 time slots in one radio block. Now, so theoretically, we can have up to 12 mobile subscribers that can transmit on one PDCH, on one packet data channels. But practically, it's only 7, because they used a 3-bit field for something called USF. And because of the 3-bit field specification, they could have up to a maximum of 2 to the power 3, which is 8 users. So although theoretically 12 mobile station can transmit on one packet data channels, practically only 8 can do that. So we saw this diagram earlier, where how the radio blocks, the user radio blocks, there are 12 radio blocks for user data transmission, and there are 4 time slot positions that are used for signaling. 2 of them are kept idle effectively and can be used for some future purposes if there was a need. Now, in GPRS, you can have different channel coding schemes. So you have coding scheme CS1, CS2, CS3, CS4, and so forth. Some of the coding schemes provide higher levels of protection against errors, and some of the coding schemes provide high data throughput. So remember, in any data transmission, if you notice that there are a lot of errors taking place in your data transmission, then your effective throughput starts to go down. Okay, so how do you get over that? You start putting extra bits of information, parity bits and other types of more sophisticated convolutional coding and so forth, so that you can recover the errors at the receiver. Now, in the process of adding these extra bits for protecting the data that you're transmitting on this wireless link, you effectively decrease the throughput. Okay, so that is this balance that you have here. So CS1 is a scheme that offers a lot of protection. Okay, it has got all sorts of extra coding that you put on your data at the transmitter, so that when the data arrives at the receiver, even if there was a lot of errors, the receiver can still obtain the original data. But in the process of putting these extra bits for protection, the effective throughput goes down. So this is the balance that you see here between CS1 and CS4. CS1, high amount of protection but low throughput. CS4, no protection against errors, or very little protection against errors, but a higher throughput. So why do we have these different schemes? Well, it all depends on the user. If the user is very close to the base station, then the data is getting through pretty well. So in that case, what do we want? We want a high throughput. Okay? Whereas if a user is further away from the base station, maybe at the edge of the cell, in that case, such a user is going to get a lot of errors in their data transmission. In that case, throughput is not the concern. You want to make sure that your data gets through with good protection. So this diagram here, again, I'm not expecting you to remember this diagram, but it essentially shows you that CS1, you basically take your data from the RLC and MAC layers, and if it is CS1, you put this phi coding with some tail, then you send it through convolution coding, and as a result of that, you're going to come up with this 456 bits that we talked about earlier, and this 456 bits is then put into the various bursts associated with the radio block. If it is CS4, which is the one with least amount of protection, you might only do cyclic coding. You might even skip the convolutional coding step and go and transmit it straight away into the different blocks. So depending on the coding scheme that you're going to use, it goes through different amount of processing before you get to your 456-bit output. Okay, here's another diagram that shows how these various coding schemes perform. Okay, now on the vertical axis, you've got throughput in kilobits per second. Okay, so that represents increasing throughput. And on the horizontal axis, you've got carrier to interference. So if there is high carrier to interference ratio, okay, that means your carrier signal is quite strong compared to the interference that you're getting. So if your carrier to interference ratio is high, then you might say something like 20 dBs. If you're getting a carrier to interference ratio of about 20 dBs, then you see that coding scheme 3 offers you the highest throughput. Okay, coding scheme 3 is giving you a throughput of about maybe 14 or between 12 and 14 kilobits per second. Okay, and as the carrier to interference ratio goes down, or the system is becoming more noisy, so maybe you get to about 12.5 dBs. Okay, in this case, the other coding schemes, like the one that gives you the best performance at 12.5 dBs is CS1. Okay, the CS1, which is the one with the highest amount of protection, it is able to get through. So maybe what's happening in CS3 and CS2 is that a lot of errors are taking place, and you are retransmitting, the receiver cannot extract the original information, and it is asking the transmitter to retransmit the information. So effectively, in that process, what is happening is that your throughput is going down, your effective throughput. So so depending on the carrier to interference ratio, you can change the coding scheme that you are using. Okay, so again, there is sophistication in that this is called link adaptation, where the transmitter and the receiver are adapting to the way the link is performing. Okay, now this is in the case there where you've just got one radio block. So if you've got n radio blocks, say if you've got 3 radio blocks, then you multiply this by 3. Okay, now it is also possible in GSM, in GPRS, that one GPRS subscriber could be transmitting on 3 time slots, not just 1 time slot, but 3 time slot. So if that was the case, imagine you've got one radio block on 1 time slot, another radio block on another time slot, and another third radio block on a 3rd time slot. Then again you've got a multiplication of 3, and that is how you get this 3rd graph here, this graph on the other side here, because it shows that you're getting a better performance. Now, one of the things that you will also see here is that coding scheme 4 never gets used. Okay, because most of the time your carrier to interference ratio is between the target carrier to interference ratio is around 15 dBs. Okay, so in that case, most of the time you're either going to use CS1, CS2, or CS3. CS4, according to these performance graphs, has the lowest throughput, whatever the carrier to. You have to get to a very high carrier to interference ratio, maybe of around 40 or 30 dBs, to start using CS4. But that sort of carrier to interference is not practically achievable in a network. So effectively, CS4 never gets used. Now you can further increase the data rate by changing the modulation scheme. So we know that in GSM you use GMSK, Gaussian minimum shift keying. Okay, in Gaussian minimum shift keying, every symbol has 1 bit associated with it. Now there is a technology called Edge, which can run on top of a GSM network, or it can also run on top of a GPRS network. Now in that technology, one symbol is represented by 3 bits. So effectively you're getting a multiplication factor of 3 for the data rates, the maximum data rates that you can achieve. So again, with this technology, again, this implies edge implies, you know, more equipment in your base stations, because you know, the standard GSM won't be able to do edge. So so it does require quite a lot of changes to your base stations and so forth. So a lot of some operators did try this out, but I think a lot of the operators didn't actually go with this technology. But some operators did use it, and they're still using edge in their network, especially in CBD areas where they want a high data rates. They have decided to implement edge. Okay, the next thing that I want to touch on is something called traffic management. So traffic management involves so the sort of things is, well, what happens when a GPRS subscriber switches on their mobile for the first time? Certain things have to happen in the network, okay? Because the first time, when you switch it on for the first time, that's the time you transmit your IMSI. After the first, when you go to your mobile shop and buy a mobile and you switch it on for the first time you switch it on, the IMSI is transmitted over the air interface, and thereafter there should not be a need for the IMSI, which is a very confidential piece of number, to be transmitted across the air interface. So because after that, subscribers get allocated something called a TIMSI, okay, a temporary mobile subscriber identity, TIMSI, and it is a TIMSI that is only transmitted on the air interface in the case of GSM. So just as you have TIMSI in GSM, you also have something called PTIMSI, or packet TIMSI, that is used in GPRS. So you have something called GPRS attach. So when you switch on your mobile, you do an attach procedure to the network, and you sort of connect to the SGSN, and the SGSN validates you, and then you stay connected to the SGSN, at which point you can, if you do want to transmit data, then you have to do something called PDP context activation, and that's the point at which you get allocated an IP address from the GGSN. Otherwise, you just stay attached to the network. So when you move around, you have to do location updates so that the network knows where you are located. And then, so you have these basic procedures. There's a procedure called GPRS attach. There's a procedure called GPRS detach. There's something called PDP context activation and PDP context deactivation. That's when you end a data session. And you also have to do, as you move around, you do something called cell update and routing area update in a network. Okay, so the routing area update procedure is very similar to the location area update procedure that is there in GSM. And then the other thing that can also happen is subscriber could roam into other networks. So how do we? These are things that, you know, if you look at a packet switch subscriber, what are the different situations that the network has to cater for? Okay, so these are the main things that a subscriber can do, and the network has to have well-defined procedures for each one of these things. So when we talk about traffic management in GPRS, there are two things that come into mind. The first one is mobility management. So as a subscriber moves around, you have to manage their mobility, because you need to do this because when there is a mobile terminated call or a mobile terminated packet, we need to know where a subscriber is located. Now, if we didn't have that information, if we didn't know where a subscriber was located, then we will have to page in every cell in your network, and that creates a lot of paging traffic. Okay, and paging traffic could chew up all of your common control signaling capacity. So you don't want to do that. So the solution to that was, in GSM you had this idea of a location area, which is a group of cells So whenever you stay within that group of cells, you don't have to do an update of your location, because the network will, if it knows the location area where you're located in, it will only page in those cells that form that location area. It's only when you move out of the location area and move into another location area, the subscriber has to do something called a location update. Now similarly in GPRS, we have something called routing area, and when a subscriber moves up from one routing area to another routing area, it has to do something called a routing area update. The second set of procedures that have to be taken care of in GPRS is called session management. So when a user wants to start a session, okay, a session management procedures are needed for that purpose. Okay, so PDP context activation. So again, the cells that you have in your network are broken down, are grouped together to form routing areas. So for example, in this case, the yellow routing area represents 7 cells, and the orange one represents 4 cells, and so forth. Again, another similar diagram. You know that the concept of routing areas in GPRS and the concept of location areas in GSM has to overlap. Okay, so in GSM, if you had maybe these two MSCs, and this MSC had one location area, and this MSC had another location area, and within this location area there were a number of BTSs, and each BTS has a cell associated with it. You might say, okay, we are going to create a routing area which is just these 2 cells, and this routing area is connected to SGSN 1, and then you have another routing area here which is made up of these cells, and so forth. So in this case, you have a number of routing areas that work off this one SGSN. So what important procedure is, if for example a subscriber, let's consider the case that a subscriber moves from this cell to this cell. Okay, if a subscriber moves from this cell to this cell, what are they changing? Well, they're in the same location area, they're in the same routing area, they're only changing from one cell to another cell. Okay, so that will result in minimum amount of signaling. Imagine if the subscriber was to move from this cell into this cell here. Okay, if these are all adjacent cells, remember these cells are all adjacent and they form an interlocking structure. If a subscriber was to move from this cell to this cell, here they're moving from one cell to another cell that are in 2 different routing areas. Okay, so in that case, something called a routing area update procedure has to be done to inform the network that this subscriber is no more in this routing area but in this routing area. So if there are any packets that come destined for that mobile, then it should be sent to that particular routing area. Okay, imagine that these 2 were neighboring cells. Okay, if a subscriber was to move from this cell to this cell, and assuming they were all neighboring cells, then that is a bit more complicated, because you're not only changing cells now, you're changing routing areas, but you're also changing location areas, and you're also changing MSCs. Okay, so because the 2 cells are being served by 2 different MSCs. So again, more signaling has to be done, because the VLR has to be updated that the location area has changed. The database in the SGSN has to be updated to say that the routing area has changed. Okay, and a procedure, the new MSC, because now you've moved into a new MSC, the new MSC has now got to go to the HLR and pull out the database information for this subscriber. So far more complex. So okay, some movements creates a little bit of signaling, some movements can create a lot of signaling in your network. Okay, so the whole idea of creating this concept of routing areas and location areas and the cell boundaries is essentially to minimize the amount of signaling amount of paging that you have to do for mobile terminated voice calls as well as mobile terminated packets. Okay, here's an example. This is a hypothetical example of how in Sydney you might have different routing areas and different location areas. Okay, so this is a diagram from Julia. So I think Julia must have got it from a Nokia source. So here you have routing area 1. So all of these cells in the CBD area all come under routing area 1. And all of these areas on the eastern suburbs or eastern part of the city might come under another routing area and also another location area and so forth. So this is what in network planning you go about taking all of the cells that you have in your network and say, okay, all of these cells will form one routing area and all of these cells will form location area. Again, you have to do it in such a way that at the end of the day, all you're trying to do is this concept is only there for mobile terminated calls and mobile terminated packets, and you have to try and somehow minimize the amount of signaling that is taking place in your network, because signaling is very important for network operations, but as far as the operator is concerned, they don't make much money out of signaling. They only make money when you make calls or receive calls. Okay, the next thing is you have something called a state transition model that is used to model the behavior of a GPRS subscriber. So initially, when your mobile is switched off, you are in a state called the idle state, which is this state here. When your mobile is switched off, you are in idle state. When you switch it on, you do something called a GPRS attach. So your mobile attaches to the GPRS network, and then you move to a state called ready state. Okay, so in the ready state, this is the state at which you can start doing data transmission, or you can start doing you can do a PDP context activation and so forth. So that's the ready state. Now, when you're in the ready state, you're sort of consuming a bit of resources in the network. Now, if you stay in the ready state for a bit of time and you haven't done a data transmission through a PDP context activation, you have something called a ready state timer expiry. So when a timer expires, after being in the ready state for a certain amount of time, maybe of the order of 15 minutes, and you haven't transmitted any data, the mobility management mechanism moves you on to something called a standby state, okay, where you are sort of consuming less resources in the network. So, and you stay in the standby state until you want to transmit. When you're in the standby state, you decide, okay, let's do a PDP context activation, and you want to transmit data, then you get moved to the ready state. Or if the standby state also expires, now this is of the order of maybe an hour, maybe of the order of hours, and that you're staying in standby state and not doing anything, the mobility management mechanism will put you on to the idle state, which is effectively the same as switching off your GPRS capability. Okay, so again, these states, you can do certain things only when you're in the ready state. You can start doing a PDP context activation, which is the point at which you start getting allocated an IP address and you start being able to transmit your data. Okay, so this is called a state transition model, and state transmission models are used a lot in telecommunications to model the behavior of various entities in your network. Okay, now we talked about PTIMSI. Okay, I'm not going to go much into TLLI this year. So for this you can just mark in your note that it's only PTMZ that is important in this particular slide. So PTMZ is referred to as a Packet Temporary Mobile Subscriber Identity. Now we know that in GSM we use something called TMZ. Why do we use TMZ and not IMZ?
It's not secure.
Secure, exactly. The IMZ is a very confidential piece of information, and you don't want to be transmitting your IMZ across the air interface, because if somebody gets your IMZ, they can do lots of things with you, with your account. So what the network does is, once a user, it's only the first time that you switch on your mobile that the IMZ is transmitted. Thereafter, you get something called a TMZ. That's allocated by the MSC in the GSM. Now in GPRS, the equivalent of that is you have something called packet TMZ or PTMZ. And in PTMZ, the SGSN allocates the PTMZ, and every time you do an attach, you allocated a PTMZ. Okay, now this is the resource that I talked to you about earlier, because only when you're in the ready state, you have a PTMZ. When you move to a standby state, that PTMZ is taken away from you. So a new PTMZ is allocated for each GPRS attach, and a PTMZ is like the TMZ in the GSM case. Now the other thing about the PTMZ is also it's only valid in one routing area. So when you move from one routing area into another routing area, you get allocated a new PTMZ by the SGSN. You also have something called TLLI, which is derived from PTMZ, and it is a means of identifying a connection between a mobile station and a SGSN. Okay, so location management. What are the different things that can happen? Okay, now in terms of location management, the network is interested in knowing which routing area you are located in, so that it can send packets to you. So here, many things can happen. You can either go from one cell to another cell within the same routing area, or you can go from one cell to another cell in a different routing area. So you need different procedures. You need procedures for movement between cells, and this is done using something called cell update. Okay, now this is a bit different from GSM because here, when a GPRS subscriber moves from one cell to another cell, it is a mobile that sends a message called a cell update message, so that the network updates the location of the cell. You can also have movement between routing areas, and this is called a routing area update. And you can also have movement between location areas, which is called location area update. And it's also possible to do routing area and location update simultaneously in GPRS. Okay, so cell update is you're moving from one cell to another cell in the same routing area. So you're inside the same routing area and you're moving from one cell to another cell. And what the GPRS mobile does is it sends something called a cell update or cell reselection message, and this is only done when you're in the ready mode. Okay, so when you're in standby mode, this does not take place, and it is in some way it is sort of similar to GSM handover, but not exactly, because the handover only takes place in GSM when you're on a call, whereas here you're not on a call. Okay, so you could be doing a data transfer. Routing area update is done when you move from one routing area to another routing area. This can be within the same SGSN, in which case it's called an intra-SGSN routing area update. If the two routing areas are controlled by the same SGSN, it's called an intra-routing area update. If the two routing areas are controlled by two different SGSNs, then it's a bit more complicated, and that's called an inter-SGSN routing area update. Okay, so if you look at this diagram here, if a subscriber was to move from there to there, okay, in this case they're within the same routing area. So this is just a cell update procedure. If they move from this cell to this cell, okay, here they are moving from one cell to another cell, but the two cells are in two different routing areas, but under the control of one SGSN. So this is an intra-SGSN routing area update. Okay. The more complex procedure is when you move between two routing areas that if this particular routing area here and this routing area, if these two routing areas were controlled by two different SGSNs, then that will be the inter-SGSN routing area update. Okay, now there's also something called periodic routing area update. There's also in GSM there's something called periodic location area update. So after a certain amount of time, now I don't know if you've left your mobile phone idle in a position, you see that sometimes your idle mobile does something called a periodic location area update. So it sort of updates its location when it's been in a cell for a long time and it hasn't moved and it hasn't done a location area update. Every there's a time interval that has been set whereby the mobile updates its location to the network. So just as you have that in GSM, you also have the same thing, same concept in GPRS. Okay, so in session management, that is the point at which a GPRS subscriber wants to connect to an external network. And in order to do that, there are three important procedures that are defined. The first one is called PDP context activation. So this is the point at which you say, okay, I want to connect to an external network. Give me the important configuration information like IP address, your default gateway, your net mask, and so forth. When you end your data session, you do a PDP context deactivation. And sometimes you might also do something called PDP context modification. So modifying a PDP context. So maybe you did a PDP context and maybe you got a lower quality of service than you wanted, and later on you want to see if you can get a better quality of service for your connection, and you can say, let's see if you can modify this PDP context activation. So in the standards, if you look, all of these mechanisms are described in detail. I'm not expecting you to be able to describe it to the same detail that they're in the standards, but you should be aware that these procedures exist. Okay, the different mobility management procedures that we talked about, and the different session management procedures that we talked about, you should know about them. Okay, and also again, we know that you can either be allocated a static IP address or a dynamic IP address for session management. Okay, now we'll just take one example and go through a little bit more detail in it. What happens when you do a PDP context activation? Okay, so the SGSN is the one that will process this. So the SGSN will receive a PDP context activation from a subscriber. The first thing it will do is it will check its database. The SGSN, just like the MSC has a VLR database, the SGSN also has its own database. And it will check its database to see if this subscriber should be allocated a static IP address or a dynamic IP address. Okay, if it's a static IP address, it will allow the subscriber to use that IP address. If it's a dynamic IP address, then it's got to allocate an IP address to the subscriber, and it has to go to the SGSN to get that IP address. Now, it also, we've already seen the concept of an APN, or access point name, which you specify when you connect to an external network, because in the context of a mobile network, you can connect to many external networks. So an access point name is used to specify which external network you want to connect to. So the next thing that you have to do, just as in GSM, you have to authenticate the subscriber. So it goes to the authentication sector, and it brings the authentication vector, and then it does the RAND challenge, and based on the signed response that it receives, it authenticates the subscriber. Then it once it has knows where the IP address has to be allocated, the first thing that it does is it goes to the DNS, and the DNS then takes the access point name and converts it to a the GGSN IP address, and then it goes to that GGSN and checks if it is prepared to accept this particular PDP context activation from this mobile subscriber, and it waits for the GGSN to get a confirmation from the GGSN, and then once that is done, the GGSN says, okay, that's fine, this is the IP address that the subscriber has to use, and then it sends that IP address to the subscriber, and then that's the point at which packets from the user can go out to the external network. Okay, so in GSM it's quite easy to get a connection started off, but in GPRS it's a bit more complicated, because the subscriber has to be allocated an IP address, and there are different types of IP addresses that can be allocated. The subscriber can connect to many different types of external networks, so the subscriber has to specify that, and then the SGSN has to check whether the subscriber can connect to that particular IP address, and so forth. Okay, say you have an Optus subscriber, this is their home network, and now they're in Singapore and they're in roaming on a Singapore network. Now, if you are on a PC connecting through your GPRS handset, there are two ways you can connect back to your home network. One way is to go through the Singapore network, through the SGSN in the visited mobile network, and maybe through the border gateway, through this inter-PLM and backbone network, through the border gateway in your home network, through the SGSN to the whatever service you're using. That's one way of doing it. Okay, another possibility is maybe through the visited networks SGSN, visited network GGSN, to the service through the internet. Okay, so there are different ways that roaming can be arranged, and this diagram shows that concept.